Welcome back to this part of the lecture. So in this part of the lecture, as I've already said at the end of the last video, I want to talk about summary statistics and I want to show you how to compute them efficiently. And this is hopefully a bit more interesting. I know the last video probably was a bit tedious, but still nevertheless we have to cover seemingly boring stuff like how to access a single part of a table or how to pull a column from a table and so on. So I hope with the summary statistics things can get a bit more interesting, more applied, and let's dive into that. And as I said, the point of it is to generate a lot of statistics. And for instance, here, as you can see, I have recreated a plot we generated in the last video, or in the last chapter more appropriately, where we use the box plot to summarize the distribution of the life expectancy of different countries in 2007. So the Gapminder package, recall that it contains life expectancy data for a lot of different countries. In this table we only looked at the data from 2007 and we tried to summarize the distribution into a box plot, or the distribution of the life expectancy into a box plot. And this is how we generated this plot. And as I already said, there's a lot of information in this plot. So for instance, this bold line here indicates the median life expectancy. And last week we kind of had to guess what the exact value of the median is. So from this picture we see that, okay, it's probably somewhere around 72, but we're not exactly sure. So while the visualization is a great tool to get an idea and to see all of it at once, at some point we'll need to compute these statistics. And this is what we can do easily with the summarize function, which is also part of the dplyr package, so also part of the data wrangling. So before we do it, a very short example on how we could do this manually. We could pull simply the life expectancy column from our table and then apply whatever function we want. So in this case we want to compute the median, so we use the function median. So my guess was sort of close. I said our median is approximately 72. 71.93 seems is more accurate, but still the picture revealed approximately good information, but nevertheless if we want to have the exact value at the end, we will need to compute it ourselves. And here we could now exchange median for any summary statistics we want. We could do median. Median is what we just computed. What I wanted to change was mean. So now the value changes. So we could compute mean, we could compute minimum, we could compute maximum, we could compute a quantile. So recall that minimum and maximum in this picture are basically the full range of these vertical lines here. I just had to think about what is horizontal, what is vertical. So the vertical line here is basically full range. So here we can see the minimum, here we can see the maximum. And the edges of the boxes are the 25% quantile and the 75% quantile. So we could compute it quantile via quantile function, and this will immediately give me back the most popular quantile. So the 0% quantile would be the minimum, this would be the maximum, this would be the 50% quantile, which is the same as the median, and then we have the lower quartile and the upper quartile here. Again, we can easily compute this, but still it's tedious to do it that way. Nice function in that respect is the summary function, which can take a tibble or a data set and give an output, given a summary of the usual statistics, so minimum, quartile, median, mean, and so on. But this summary, it's an old function, it's from base R, so it's not a tidyverse function. It's still nice because you get a quick overview, but you cannot work with this data. We cannot really extract the data from this because this output here is a string, and then you would need to figure out how to get to it. And the point is, it's not really easy to work with that, so instead we can use the summarize function from dplyr, which does not have a default summary. So if we do this, we will basically get nothing. So summarize forces us to declare manually what statistics we want to do compute, but it also gives us a lot of power, whereas a summary also has nice default values, but we cannot really change much. So let's compute a few summary statistics. The syntax is pretty easy. Declare what you want the column to be named, so the mean of the life expectancy column. So we'll get a column which will be the summary of the mean of the life expectancy. So basically, if we execute this, the column name is declared here, and same as with mutate, we equal this to whatever operation we want. We're not restricted to mean or whatever. We could add +2 here if we want, which is of course not really a useful thing to do here, but nevertheless we have a lot of options. And in this way you could compute a lot of statistics, and you will get them in a neat tibble. So now you could easily access that data. I don't know. So if we want to access a single element here in the pipe, and with a pipe you will need the dot operator, and then say, okay, you want what do you want? Just the third column, then you will get this. And as we've learned before, with double brackets we get that value. Point is, the summarize function will give you back a tibble, and this will contain the data, and you can easily access the data. Similarly, as mutate, summarize works great with across. So for instance, if you want to compute, as in the summary function, if you want to compute the mean for a lot of variables, so for, in this case, GDP, population, life expectancy, just for these three, then you can use the cross function and don't have to use mean, have to declare it manually every time. So let's do that. So summarize, and then across. Alright, which columns do you want? We want to use life expectancy all the way to GDP per cap. And the function we want to use in this case is mean. You could also use multiple functions. So here, if you take a vector and say, okay, you also want to use median, then you will get both the mean and the median for each variable here, and you can actually change the name here. So the naming is with first an underbar and then 1 or 2. You can change the 1 or 2 to the actual name of the summary statistic or to some other name you want with named vectors. which you will do in the exercises. And then with a combination of pivot longer and pivot wider, you can actually transform this so that it's you will get a summary that looks more like this. So you can actually do a lot with that. Okay, so let's run some other summary statistics. As I said, we really we have a lot of options with Summarize. We can declare any function we want as summary statistics. For instance, if we want to find out, okay, in 2007, how many, what's the percentage of countries that had a life expectancy less than 50? Or a mean life expectancy less than 50, or say 60. So let's say the percentage lower 50. It's quite easy to compute that. We can simply compute mean of life expectancy less than 50. So what we do here, or what Summarize will do here, it will run life expectancy, or will take the column life exp, check which row is less than 50, and this way we'll get a column of true or false values, and the mean function will convert that true or false to 0 and 1, 1 for true, and so the average, the mean of these values is simply the percentage we are interested in. And similarly, we can do it with 60. So yeah, here we see that 13.3% of the countries in 2007 had a I think mean life expectancy less than 50, and similarly 30% of the countries had a mean life expectancy of 60 or less than 60. Yeah, so this is maybe also a good time to illustrate the difference between Summarize and Mutate. You might think, okay, they feel the same, why are the two different functions? The point is Mutate works vectorized, Summarize works also vectorized, but the point is Mutate expects a vector and returns a vector. As you can see here, Summary expects a vector but returns a summary value. See, because each time it only gives back one value. If you, for instance, use Mutate here instead, and say you want to run the exact same thing, then of course you will be able to compute that value. The value will be the same, you see it here. This was the value we had originally, but Mutate expects a vector back. So again, because you only get one vector back, one value back, it will recycle it to fill that to fill the column. And this is, I don't want to say more or less, but this is at least a huge difference between Mutate and Summarize. So just keep that in mind. And if we look at these summaries, we will see that we will notice that, of course, this analysis is pretty coarse. So it's not fine-grained because there's no differentiation between countries or between continents. I mean, countries doesn't make much sense to differentiate between here, but at least with continents, there would be it would make sense to differentiate between that, because as we've already seen in our visualizations of that of this data, there is differences between the continents. So we should run a similar analysis here, and we should compute a summary for each continent. And to illustrate how we can do something for subgroups, let's first start with an easy summary statistic, which is just the count. The n function here simply counts the observations within a group. In this case, we have all the data here, so it's just one group, we will see that, okay, we have 142 observations. So maybe we can look at the documentation. So n gives the current group size. Because I have all the data, there's one group, and I simply get back one value. But now, as I said, we should make our analysis more fine-grained, and this is why we can use a grouping argument with the function group by. This is also really a nice way to demonstrate how the pipe works well with all of these functions, because here you can in the step see, or here each step can mean one specific thing. In this case it's simply grouping. It's not really an important step, so we wouldn't want to jumble it into one line if we nest the code, because this won't be legible. But here, if we use the group by here, it actually gives us a lot of information, because now, okay, I see it's grouped here now, so this is a fundamental step in our analysis. I'm not sure that my explanation just now was that great. In any case, the pipe here, in my opinion, helps to structure the code, even though they are group by functions which don't do a lot for our analysis. They are important, but in the code they're not that important. I mean, they don't have that great value. In any case, pipe works well here. So here, let's say we want to group by continent. And if we do that, then we'll see, okay, now there is a grouping, and the n function will count the observations in each group. And basically this is what we can do with any summary. We can do group-wise summaries of anything. So in this case, we could run these compute these statistics for each group. And if we do that, we'll see, well, we get exactly what we would expect. Each statistic is computed for each grouping. In fact, we can even use more than one grouping. For instance, we could use the whole data set. So let's just say, let's just put it into a new chunk. Let's say instead of only the 2007 data, use the whole data set and group additionally by year. Then you will see you get a new year column, and for each year you will have a mean life expectancy. So we could, for instance, save this in a variable as called summary evolution, because this helps us see now, okay, we could visualize now something like, okay, what is the development or the evolution of the average life expectancy for each continent. This is something we could do with this data now. Also, it's always helpful to have the compute the n or the amount of observations too, because this will help to avoid making conclusions with small sample size. If you group a lot and you're not careful, you could end up with computing a statistic for a really small group, and if you later use that value in a interpretation or whatever, you have to be careful that your sample size might be really low and your interpretation might not really be valid. So it's a good way to have this in here. In any case, I saved this tibble now as summary evolution, so that we or more importantly, more appropriately, that you can plot it. Later on I will show you what it will look like, what the plot will look like, but the implementation you will have to do in the exercises. In any case, now that I've saved this tibble, I can see that actually there was another output of Summarize. After, I mean, here I saw only the tibble, but if I look into this window, the message was there all the time. In any case, this tells me that the Summarize output is grouped. So here the output is now continent. The grouping of the output of a summary evolution now is continent. And we will talk about what kind of implications that can have in a few seconds. But if you don't want to get this message and you don't care about later grouping anyway, which is often the case, you don't want to use any grouping later on, you can simply declare groups should be dropped. So basically, this is what this part here means. You can overwrite this using the groups argument. And then there is no message anymore. In any case, this data here now can be used to plot or to visualize the evolution over time, and this is what it will look like, what it could look like if you want to visualize this evolution. Here the area, or the shaded area, indicates the values from the 25% quantile and the 75% quantile, so the range in between. And the solid line is the mean of the life expectancy. And so here you can see for each continent how the average life expectancy evolved over time. Okay, so this again you will do in the exercises. Let's talk more about this grouping issue. So, as I said, if I don't use this groups argument drop, let's drop it, then I will get a message that indicates that this new that summary evolution is a grouped tibble now. And what problem could arise? Well, say you want to get the first row of this tibble now. So what you would expect is if you throw this into the slice function, then you would get exactly one row back, because you said, well, here you only want to have the first row. But the problem is, because this is a grouped tibble now, and slice, if you look into the documentation of slice here, it says that a slice can work with a grouped tibble. So this means it will perform the slicing for each group. In this case, it will give me back the first row of each continent. Similarly, if I do why is this not working? Why do I not get more groups? Weird. In any case, this should work. If I do n is equal to 3, it should give me 3 for each continent. Well, it doesn't matter. In any case, point is, slice behaves differently than what we would expect, and this is why you need to be careful with that, and this can have some different implications. For instance, if you were to, let us look at something else first. So in the last chapter we computed a few box plots. Again, these were summary statistics, and there we generated this plot here. And as we saw, there are these 2 points, and so they are outliers in this picture. So they are kind of extreme values in that in that continent. And as I said in that chapter, we can easily extract it, and this is where grouping can actually be helpful. So we want to do this, and we want to extract the extreme value or the minimum value for each continent. Then grouping could be something we want to use. So if we take the table 2007 and we group it by continent, then we can use slice min with life expectancy to get the country with the lowest life expectancy for each continent. So here the grouping was really neat, and slice actually did what we wanted to do. So what continents were these? This was Americas and Asia. So Haiti and Afghanistan were our were the outliers we were considering. I just noticed, I think in the lecture notes I have written Swaziland and Haiti. It's not completely, it's not really correct. I will correct it, well, soon, I hope. In any case, here this grouping was helpful with slice, and the different behavior for group tables was actually to our advantage. Similarly, not only slice works with group tables differently, but mutate as well. So for instance, if we look at our summary evolution table again, and we want to compute the mean of the lower quartile, so let's just call this new column or new col. It's just for the sake of demonstration, we compute something. So here we compute this part here, and if we only look at one, then we can see that the mean of the lower quartile, this new col, is actually not a single value. As we've seen earlier when I was showing you the difference between summarize and mutate, if you run basically a summary with mutate, then the value will get recycled and the same value will be within each row. But here what you can see is there are actually different means computed, and this is because mutate also understands grouped tables and will, if you run something like that, same as summarize, will do the computation group wise, and in this case it computed the mean of the lower quantile or quartiles by group here. So that's something you will have to look out for. Similarly, a filter also works differently with grouped tables. Basically it works like a grouped mutate function followed by an ungrouped filter. I really rarely use it, so I don't want to explain it that much. If you want, you can look into the lecture notes, or if you ever feel like you need a grouped filter, then you can also, in this case, look into the lecture notes. Here I will simply skip it, so that we can look at different data and other important topic, which is how to combine data. So for instance, let us look at the NYC Flights 13 package, and this contains the flights dataset. And this dataset is basically information on all the flights that departed New York City from one of the 3 airports, so JFK, JFK, LGA, or EWR. I kind of forgot what the name stands for. In any case, before we move on, let us only work with a couple of those variables, because there's a lot in here. and I don't want to work with all of this. So flight selection, let's call it that, and we will select everything from year to departure time, and we want to get the origin and the destination. So this is the data we want to look at now, and as you can see, the origin is always one of JFK, LGA or EWR, because this data set contains all the flights that departed from there in 2013. Okay, so because I forgot what EWR and LGA stands for, I would need to look it up, but luckily this package, the NYC Flights 13 package, comes also with additional datasets airports, which contains the FAA abbreviation. So this is the FAA abbreviations, and each airport has one. So here I could look up what these abbreviations stands for. In any case, there's also even more information here. So the location, so latitude, longitude, altitude, and so on, and the time zone, more importantly, which is something which becomes important once you want to deal with the duration of a flight, because then you will have to consider, if you only have departure time and arrival time, then you will have to consider how many time zones you were flying through. So in this airports table, there's a lot of useful meta information, which is called, so useful additional information which can help with analysis later on. Here I only want to use the names, so I only want to use FAA and name. And then I want to rename, so origin should become FAA. And why did I do that? Because I want to have this column and this column be named the same, so that I can join these two tables together with an appropriate function, and I will use this origin column because they have the same name as identifier, so I can get the name, the appropriate name for each airport in here. So let's save this as airport names, and now I want to join via the origins. So let's take flight selection, and then we will use what is called a left join. Left join is one of 4 join functions, so basically it joins two tables or two tibbles, x and y, and depending on what join function you use, it will either include all rows of the left table, so of x, or all rows of the right table, so y, and inner join and full join include that are either in all rows that are in both tibbles, or all rows that are in either tibble. So in any case, here left join is what I want, because I want to keep my original flight selection tibble and only add the appropriate names to my tibble. So here I will simply say, okay, join by airport names. Because I use a pipe here, the first argument, so x will immediately become what I've used here, and y will then be this second tibble airport names, and we will need to declare what to join by. In this case we will use origin as identifier, and here we can see that the name was added to this tibble according to what airport we were departing from. So in this case, EWR stands for Newark Liberty International, LGA stands for LaGuardia, and JFK for John F. Kennedy International. Okay, so this is one way to join the table. Let's join the names for the destinations as well. So we have here the abbreviations for the destinations. So let's save this intermediate step. Origin join. And now let's do a destination. Let's do the same thing for destination. A different way to join this is to use airport names, but because airport names now has origin, I don't want to rename it again. Here I kind of said, okay, use origin as the common color, so as ID, and then join. But now I want to link, I don't want to rename this column here to dest now for destination, so that I can join it with the destination column. So instead, the left join also offers a different way to join, or a different way to specify the identifier. So we want to use airport names again, but we want to use named vector to this to do this. So we want to use link destination to origin. So a named vector here, as you can see here, is here's the name of the vector, and here's the value of that vector. So this is a named vector, that's how you declare it. And with a named vector, you can tell left join how to relate two differently named columns together, or related to each other. And as you can see, because both the name column now, because after I join, or the name column is in both origin join and in airport names, this join function will keep both of them in here and just simply add a point X or point Y at the end. And now we can simply use mutate to, for instance, if we want to rename origin and dest to the full names, we can simply use a mutate to do this. So origin should simply become name of X, and destination should simply become name of Y. And yeah, let's just do this. Now we see we have the appropriate names in name and destination. And there is a missing value here, but we don't need to worry about this now. And because I don't need the name X and name Y column anymore, I can simply throw that out. So throw out name X and name Y. Okay. So this is how you would join two tuples together. And also what you can also do, so here you were joining by joining tables or data together by a specific name. So you would telling R to figure out, okay, I have this identifier here, figure out what is the corresponding value from that table and bring it into my table. And what you could also do, what is something you sometimes even need to do, is combine data from different sources by simply sticking them together. Don't need to look up anything. You just simply either need to add columns or put the tables together, so that because they have the same amount of rows, you can simply put them next to each other. Or if you have two data sets which basically deal with the same data, so the column names are the same, then you want to combine these two into one big data set, so you can simply add the rows together. So then you will have the two data sets below each other, and basically what you're doing is you're binding either columns together or you're binding rows together. And the two appropriate functions for that are bind rows or bind columns. Both of them are documented here in the same on the same page. And of course, if I want to add new data with bind rows and bind columns to the flights data set. To do that, I will need to get create a bit of fictitious data. So here, let's create a sample column with flight numbers. Say I want to label all the flights from 1 to, 336,000, just in the order they departed in 2013. I can simply create an appropriate column and then later on add it with bind columns. Of course, you could do this with mutate too, but here I will do it with binding just for demonstration. And also I will need a sample row, so I will need a fictitious flight I can add to my flights data set. And here I have come up with some random flight data. In this case, it's a flight from Ulm to Oberdischingen Ulm is the city I'm living in, and Ulm Oberdischingen, and Oberdischingen is a small village. I don't think it's too large here. In any case, it's in the vicinity. This is the fictitious flight, and we can add them to flights. So now we have this, and we want to first bind the columns, and we can easily say, okay, the new variable name that we add to it, flight number, is given by this vector. And now we see that in this data set we have a new flight number here. Also, I need to use flight selections. There are way too many variables in here. So here, this is my new column, and now I can also bind the rows with my new flight variable. And it's at the bottom now, so let's arrange by flight number. So this arrange will help me to sort the data, so the observations are now sorted, and we can see our flight here from Ulm to Oberdischingen is in the data set now. So basically, this is how you would use binding rows and columns. Okay, so let's do something more interesting. Let's use this flight data to run a small case study to combine a lot of things we have learned throughout this this lecture. So first of all, let's look at the delays of the flight. So let's create from flights, let's select a few variables, in this case from year to departure delay. So my table has this information now. And first of all, if I run a data analysis, I will need to check that my data is actually complete, or I have to check if there are missing values. So with the is not a value function, I can check whether there are missing values. So for instance, is NA checks if there is a missing value, and if it's a missing value, it will say it's true, will return true, and otherwise it will return false. So for each column, I want to apply this function now. So here in each instance it will tell me if this is if there is a missing value there. And with Summarize I can simply compute the sum of these true or false values, and this will tell me if a column, or if how many missing values a column contains. What's its problem? Oh, I've misspelled across. So here we see that the departure time and departure delay is contains missing values. These are probably relating to flights that didn't actually happen. They were probably scheduled, but yeah, they didn't actually depart. So for our purposes, let's simply ignore those. Let's look at only the delays of the departed flights. So simply filter them. So departure time. And if I check delays department, now there are no missing values anymore. So I can work with that data now. So let us take this data to compute a few summary statistics. So in this case, for each day, I want to measure the fluctuations in delay. So I want to compute key quantities of what's the minimum delay, what is the maximum delay, and I want to compute this for each day. And this is where summary or the summarize function comes in. First we will need to group though. So we will need to group by year, month and day. So this will be my grouping variables. And then I can simply do a summary. So for simplicity, I simply copy and paste this from the lecture notes. I mean, you know how this works now. So here we have all of the summary statistics now. But if I want to visualize the summary statistics over time now, I will need to use these as, we need to have those as rows and not as column names. So I will need to use pivot longer to sort or to rearrange the data. So I need to use everything but year to day, and then the values should, I will just simply use a name it value, but the column names, so these I will put into a column summary. So now I can easily plot this, or not quite easily. One step is missing. I will need to get a date column. So because if I want to use my x-axis as time, I will need to convert this information to a date, and the LibreDate package has a function that helps me with that, which is make date, and then I can simply supply it with year, month and day. And now I have a date, and also a date format, which is neat for plotting, as you will see in the exercises. So let's save this in summaries delay, and let's plot this. We should plot all but this n here. I want to figure out the amount of delays and not the amount of delays or of departed flights. I want to figure out yeah, what's the minimum of the delay and so on. This is why I filter here. So summary should not equal to n. So I got rid of the n summary, and then I can use Ggplot as before. To save time, I'm simply copy and pasting it. By now I think you know what the code does. So here I use my date as x variable, the value of the statistics as y aesthetic, and column aesthetic is given by the summaries. I'm trying to draw lines, and then I'm faceting, so each summary is in a different window. And then with the scale x date, I change the labels so that it displays the month number, and then I change the labels a bit. So here, here I can see now that it's really volatile. My data is really volatile, or my summary is volatile. So let's try to run gmsmooth with it to get a better picture of what is actually going on there, so to ignore the noise a bit. And also what I would like to do is to order the windows a bit, because I would like to have minimum as the first window and maximum as the last window, and then have this in ascending order. We can do it by changing the summary column so this column to a factor, and then giving the order or the levels of the factor, and then FacetWrap will automatically arrange it in that order. So our summary levels are this. This is the order I want to use. So first the minimum, then the lower quartile, and so on. And then I can run the same plot again with the additional step of mutating. So here I simply reformat summary as a factor with the specified levels. And also I make the original lines smaller. Not smaller, more transparent, so that the data is still in there, but it's not dominant. So that the noise can still be seen, but it's not dominant. And gmsmooth is the line I actually want to plot. So I want to get a smooth line through my noisy data. And with this span argument, I can kind of differentiate, okay, how much should it be smoothed and how much should it be smoothed. Depending on my value, the corresponding line will be either super smooth or not smooth at all. It's not really an exact science how to pick this value here. I'm just pick this value to still capture a bit of the noise, but still have some smoothing in it. Basically, it's so that I can still see something in a picture, so that it's smooth enough, but I don't have smoothed out anything, so that I can still see a bit of the noise. And if I run this, as you can see now, my facets are sorted here, and yeah, this is the plot I would get if you, for instance, say span is equal to 0.5. Then you see that it's much smoother now, and the higher span is the smoother it is. But as you can see, if you do span too large, then it's, in my opinion, too smooth. You cannot make out a lot of characteristics from these plots. So this is why you will need to try to find a good a good trade-off there. Okay, because this video is already quite long, I will skip the interpretation of that. You can read it in the lecture notes. But a different, but if we want to look at some more of these plots in more detail, we could always filter out a couple of more statistics, and then not only the end statistics but others as well, so the extreme statistics. And also often it helps to look at the median instead of the mean, because it's smoother, it's more robust against outliers. So here in this case we could get a better feeling about the delays. For instance, we could see that there's a huge spike of the delays at the beginning of July, which corresponds probably to the beginning of the end of the school term in New York. So this is why there are probably a lot of people traveling, and this is why there are also, as a consequence, more delays. Okay, in the lecture notes you will find a second analysis with respect to weather data, which is also part of the flights, not of the flights package, but of the NYC. NYC Flights 13 package is the weather data, and there you can find a lot of data that is related to weather. And if you combine this with the delay data, maybe you can find some connection between the weather at that time and the delay that occurred. And yeah, for time reasons or due to time reasons, I will simply stop the video here, or I will stop this case study here, because you can read the rest in the lecture notes. In any case, in summary, data wrangling is really about generating questions or generating or diving into the data and generating questions to answer. So in this case here it wasn't like a really specific question, more of a broad, okay, let's look at the delays. Is there something we can say about the amount of departure delays? And once we have dived into the data and, for instance, looked at this plot here, we see, well, there are some spikes there. Why is there a reason for them to be there? And then we can dive into that question next and try to combine this maybe with the weather data and see, okay, on that specific day there was, I don't know, a huge storm and this is why everything was delayed. Or in this case, we were looking online at the school schedule and see, okay, this is probably due to the school term ending, that there is a huge amount of delay. But in any case, we try to make our questions more specific as we go, and in the end we try to understand what is happening in the data set, or what we can find or see in the data set through questions like this. And data wrangling is an iterative process of having a question, trying to run a few or compute a few statistics, computing new variables, visualizing them, and then generating new questions, and then doing it all again until at some point we say, okay, I've had enough, I think I understand what's going on here, try to put this into, formalize this with a model or something. And this is something we will then we will deal with once we talk about models later on in this course. So for now, I think that's all I wanted to cover, and then I will see you in the next video. Bye.